Hello, good evening, everyone. My intention was covering Microsoft Power BI, the desktop version after predictive analytics, because this class consists of students from different majors. Some of you are, let's say, from accounting, MBA, and other majors, and most likely for your project, you need to know a lot about predictive analytics. So I teach predictive analytics ahead of time a little bit, so it could help you for your project. Then at the end of semester, for hopefully you have enough time, I go over some extra stuff like Microsoft Power BI. So that's a part of your class, but I'm going to cover later because for your final project, Tableau and predictive analytics should be enough. Therefore, it's a bit change of the schedule on your syllabus. Any question from previous assignments or any other thing? So just keep in mind there's three tools coming. Homework 4, homework 5, both are on campus. Also Moodle, both, and also you have first project delivery by September 20. Again, as I said, for your final project, it's okay if you change your topic in the second or third delivery, but don't miss the due dates. Okay, this week I start talking about predictive analytics and its application. We go over some data mining standards, and also most likely next class we start working with 9. So for predictive analytics, I teach 9 in this class. Basically, there's a lot of similarity in predictive software or programming languages. So if you are happy with Python or R, you can, for this section, instead of 9, you can do it through Python or R. However, if you're more than welcome to do it through 9, and I think it's pretty easy and straightforward. For who has different background, 9 just basically you do programming activity by drag and dropping some modules, so it shouldn't be very difficult. In this class, I'm going to cover some of concepts and basics that you need to know before working with 9. Please download and install 9 software, which is KNIME, for the next class. So in the next class, when I do some hands-on experiences, you can just follow me. And it's a free software. So just see, you go to just Google, download 9, either Mac or Windows, that also should be fine. So you put your information. So just download the installer one. I'm using Mac or Linux, that you have other issues done with the other versions. So download install shouldn't be very difficult. Just after download, just press next, and install the software. So next class, when I go for hands-on experiences, you can follow me. let's watch this video and then we have a class discussion about the technology and artificial intelligence such as IBM Watson affecting the number of analytics jobs or not. I think I should share some.
I remember that morning going to the lab and I was thinking, this is it. This is the last Jeopardy game.
This is Jeopardy, the IBM Challenge.
Here we go. Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
Four-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
After the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just going to run the whole board on us.
Watson.
What is shoe?
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right, and with that, you move to $36,681.
So you got the point. I mean, there is some actual people competing over Jeopardy game with the IBM Watson artificial intelligence. So Watson is just the name of their artificial intelligence project.
The risk was, Ken gets a daily double, bets big, gets it right, he's going to be well ahead. And then with that kind of lead going into Final Jeopardy, if he bets enough, he could end up winning the match.
Ken.
What's a committee?
We got to find that last daily double. We got to find that last daily double.
It was a crucial moment in the game. There was still a daily double on the board, and it was starting to become pretty clear that it was in the legal ease category. Let's go to legal ease for 1,200.
Watson.
What is executor?
Right.
Same category, 1,600.
Answer, daily double.
That was the moment when I knew it's over.
The category is 19th century novelists.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Now we come to Watson, who is Bram Stoker, and the wager. Hello, 17,973, and a two-day total of 77,147.
I would have thought that technology like this was years away, but it's here now. I have the bruised ego to prove it.
My past Jeopardy experiences have been great, but they weren't really weighty with this kind of technological, philosophical importance. I think we saw something important today.
Didn't really think very much about the implications until later and say, wow, wait a second, this is history.
Of course, this whole project is not ultimately about playing Jeopardy. It's about doing research and deep analytics and a natural language understanding. This is about taking the technology and applying it to solve problems people really care about. We're just so excited about all the things we can do with this.
I had thought this is the end. We get there, we're done. And I'm realizing it's just the beginning.
The IBM used to be very heavily focused on the hardware industry. Now they are much more in the software industry. So, okay, what's your idea? Is technology and artificial intelligence, such as IBM Watson, affecting the number of analytics jobs? So some of you are doing business analytics, or even you might, or some of you might be different majors, but still you need to do some analytics. What's your idea? Anybody has an idea?
a lot of research-based jobs could be?
I think at the end of it, you still need a human mind to give solutions. A computer can give you like the result of some processing, but it can't make a decision for you. But the end thing, you still need a human to make that decision.
So any other idea?
Develop AI like Watson, it definitely requires a lot of human brains and a lot of research and everything. So at the end of the day, Watson will only be able to learn after a lot of years of training the data, and the AI requires time to catch up to the speed.
Yeah, there might be different ideas. So some ideas, some of your friends thinking that it might be some other opportunities, and also there might be some decision makers. I've also looked at other people's idea. Somebody thinks some basic analytic jobs might be done by artificial intelligence eventually, but people who want to do analytics, probably they need to look for new skills that are that could be available soon. It's some like comparing the horses with cars. So cars technology eliminates some jobs related to transportation by horses. Those jobs are eliminated, but more advanced jobs are available through the car industry. Something could happen, so who knows, but I just want to know your ideas. Okay, so basically we have two major groups of data scientists or analysts or analytics translators. So basically there are two groups of people. One group focus on techniques and how to discover data, and the other groups mainly focus on how to use the data. Let's say somebody from finance or somebody from marketing, probably they can communicate with people who are analysts, so they can do a group project. One group will have more focus on the data domain, and another group could focus mostly on algorithms and how to process the data. These two groups of people need to communicate. So one goal of this course is you guys to understand how to communicate with the domain people. Fortunately, we have some people focus of marketing and finance or MBA. So maybe you can make through your group project, and if you focus on their expertise, you can understand that it should be a way for you to be able to communicate. So you, even if you're deeply in the data science or data analysis, or you are expert in data analysis, you might know many advanced techniques such as database management, working with Hadoop, or some advanced algorithms. Still, you need to produce something that some good reports for the people who are data, who are expert in the specific domains. But at the same time, people who are expert in the domain, they should know what those guys mean. When they talk about prediction, when they talk about some association, what do they mean in general? But they don't have to be expert in some certain algorithms. So 9 actually is mostly good for analytics translators. So people who has some expertise in their own domain, so they don't have to know too much of algorithms and basically working with the big data. So you guys can work with the 9 and you can do very interesting predictions or finding some associations. So this 9 helps you guys to practice and understand what those concepts mean. Okay, so we have a family of data mining, machine learning, artificial intelligence. There is some definition for each of them, but the border is so pale that somehow you can consider it could be kind of equivalent. So when people are talking about like algorithms and data mining, machine learning, or artificial intelligence, there might be some similarities. Sometimes for some people it could be exactly the same. So although there is some definition for each of them, but based on what I saw, they're from the same family. And many times, what people need from machine learning is pretty much similar to what they need from artificial intelligence. So, but at the end, the goal of this predictive analytics is finding some pattern, finding relationship between the data. There's different types of patterns: association, prediction, cluster, and sequential relationship or time series. Any questions so far? Also, there is some well-known techniques or algorithms. I'm pretty sure you have heard of linear regression and logistic regression, also in your undergrad. So for some advanced associations, pattern, we use neural network. So and you might know if you have several hidden layers, we call it deep learning. So deep learning basically is the more advanced version of neural network. Supervised machine, k-means neighbor, decision tree, they're general algorithm names. Again, at the end, you don't have to know the basically you don't have to know the details of the algorithms. Just consider them as a module that you just input the data and get the output with the prediction. But even for linear regression, there's a mathematical proof which is actually really difficult. If you are from mathematical backgrounds or some engineering majors, they prove linear regression. Frankly speaking, the mathematics behind linear regression, I think, is much more harder than neural network. Is actually, but when you want to do linear regression, you don't look at what is the details of linear regression. You just see a line as the outcome of model. So if you are able to do linear regression, probably doing supervised machine neural network shouldn't be very difficult for you. Still, you don't know what is under the hood of those algorithms. As long as you can use them, that's good. Generally speaking, we have two types of learning, supervised and unsupervised. So for supervised learning, you know your dependent variable or your target variable. Sometimes instead of dependent variable, we call it target variable. Let's say you have historical data of Bitcoin. So your model has some independent variables, maybe volume, number of trades, maybe exchange rates, oil price, or some news information. And the dependent variable target is the Bitcoin price. So you have historical data to train your model. And at the end, you want to predict a target or dependent variable. So this is supervised. Unsupervised learning is basically you don't know your dependent variable. You just have a bunch of variables and you try to group your observations based on some certain characteristics. One of the best applications might be YouTube ads. So based on the videos that you have seen and the cookies information that are on your system, YouTube could decide you belong to some certain people and show you some specific ads. Like for example, if you see so much of like sport videos, maybe they show you something about vitamins or like some proteins. Or if you watch some, let's say, if you look for some certain foods and you watch some like videos about how to make some certain foods, maybe you're belong to people who are more looking at how to make some food, and that's more interesting to you. They show you like different pots or like cookers, so they think you belong to different types of people. So in this type of learning or training, they are not looking to predict something. They are to try to segregate people based on some certain characteristics, and then treat those groups differently, like as YouTube ads. And here I put this taxonomy of data mining algorithms, or again artificial intelligence or machine learning. So prediction, association, segmentation. So by the way, you don't have to memorize it. I just want to show you, those classification things. So for prediction in this class, we cover at least classification and regression. For association, we cover at least market basket analysis. And for segmentation, I think we have enough time to cover clustering. So I picked some of them, and the one that you most likely need for your final project. If your final project is, let's say, sequence analysis, and you need to study some other algorithms or time series, so probably at the end it's not the big differences. You just use some modules to do different predictions. So do you think visualization could be a data mining task or not? And why?
Because there are some tools which will help us do the data mining and visualization on the same platform. But like if you use Excel or if you use just an Access database, so we only do data mining in Access, we can run queries to extract data, and we can use another tool where we use it for visualization, like Excel or any other front end. So, but if you use Salesforce or Tableau or QuickBooks, so we can access that. You can actually connect the Tableau to your backend database and do both data mining and visualization on the same tool.
Yeah, you're right. And if you might remember, you put some examples. We look at bank accounts in the Britain, and maybe through visualization, you can find some association between, let's say, age and the bank balance, or let's say from gender and like their balance, bank account balance. So essentially, it helps you to find some association. So which you might remember. I think earlier over there. So findings, it helps you to find some pattern and association. So that could helpful, but those like through the visualization, usually the association that we find is kind of subjective, but it's still very powerful and very fast. So data mining versus statistics. Based on this figure, do you think they are same or there could be some difference? So as you see this figure, it's my mouse. So regression is within data mining algorithm, which is a statistical algorithm, or ARIMA, autoregressive methods. So basically, the statistical algorithms or models that you have, they are a part of data mining. But data mining has a larger umbrella in terms of predictive models or association models. So neural network, support vector machine, k-means. So it covers more algorithms. So statistical algorithms that you use for prediction or finding association, there could be under general data mining umbrella. So basically, if you want to use a statistical model for prediction, association, or clustering, so they are tied to statistical conditions. For example, let's say for regression, your data should follow normal distribution. So, or let's say you want to do picture classification. So for if you Google, you might see some people use data mining algorithm to look at X-ray pictures and try to say if certain people have COVID or not. So the data doesn't follow any statistical conditions that you need their pictures. So for those, because the statistical algorithms has some certain limitations, on top of them, we use other data mining algorithms that help us to look over non-linear relationship or some other applications that are not relevant to statistics, such as image processing. Any questions so far?
What is moving from art to science for DM project?
Could you say again, please?
What is moving from art to science for DM project?
You're saying we are moving from art to science?
Yes, just the third sentence.
Oh, art to science. Okay. I haven't started this section, so I was thinking you're asking the first one. Okay, here I'm talking about the standards. So instead of randomly creating a project, it's better to follow some standards. In art, you follow your basically. For artists, if it's art, it means it doesn't have any standard. So it's based on your creativity. You make something, right? But for data mining project, we want to have some certain standards. So we follow some steps, some scientific steps to produce to be able to produce some insights. It's what we are talking about. So having said that, we want, let's say when you want to publish a report or paper, everybody should understand what was your steps. And again, science also means you should be able to reproduce those outcomes. Having said that, we follow some certain standards. So when we talk about certain steps, everybody knows what we are talking about. So there's these Christian, Sigma, and KDD, they are major standards that everybody follows, and there's basically a lot of similarities between them. Okay, so Christian is the most famous one, cross-industry standard process for data mining. It has 6 steps. First step is business understanding. So it's basically domain knowledge. For example, let's say you want to predict, you want to look at X-ray image and try to predict somebody has COVID or not. So business understanding here means medical knowledge. In those certain projects, you need to work with some doctors, medical doctors, and their medical knowledge is business understanding. Data understanding. So again, X-ray images, you need to know basically image formats. What kind of form? Some pictures are in 3D, some of them are 2D. Data preparation. So you might have some noises for some like variables, you may need to convert to different formats. So this account for data preparation. Some cases you want to get to the outliers. So usually this accounts for 85% of your time. Model building and evaluation usually remaining 15%. So although we talked about some advanced algorithms, but they usually take like 10 to 15% of your time. So I expect same would be for your class project. However, your class project, you usually Google some data resources through some websites such as Kaggle, KD Nuggets, or UCR. Usually they took care of data preparation and most likely data understanding. So maybe you need to have some kind of business understanding, and also on top of that, you should do model building and test and evaluation. So again, for X-ray images of COVID-19, so you need to use maybe deep learning to look over images, and your algorithm would learn what images associated to COVID. In test and evaluation, you introduce new pictures, and they look over those pictures, and they can basically predict if it's associated to someone with COVID or not. And also look at this figure. This is actually the reality that could happen for your project. So you have business understanding, which is domain knowledge, data understanding, and data preparation. So as you say, some like back and forth links. So some that go forward, some that goes backward. Basically, let's say you work with a medical doctor, you take X-ray images and you prepare them, and then you apply neural network and you make model. But in test and evaluation, let's say your accuracy is 60%. So it's too low. 60% is near 50%, near tossing a coin and just randomly saying which one has COVID, which one doesn't. So it seems your model is not good. So if in test and evaluation you're not that much happy, maybe you go backward. Maybe you change your model. Instead of you work with different types of neural network model. Maybe your data prep is bad. Maybe your images it has some noises. Again, you go backward and change, work on the images and try to improve your image qualities. So you go back and forth a lot until you reach a certain accuracy that is satisfying. I think for COVID-19, I look at some papers, they are near 95% accuracy. So if you think your model reached as some acceptable level of accuracy, then you can deploy. So then you can give the code to, let's say, doctors, and they just, each time, they just show the X-ray image to those models, and with 95% accuracy, they predict if someone has COVID or not. So in this case, data mining helps doctors to make a more informative decisions. So maybe they look at some medical tests, so which like we do it almost every, not, I think we do it twice a week or once a week if you're vaccinated or not. So on top of that medical test or lab test, they can have X-ray tests, and then they could have a more informative decision. But basically, you don't want to tell doctor what they should do, and you don't want to get sued by different people, because at the end I said 95% accuracy. So for 5% you made mistake. So just keep in mind for any major, more specifically something related to human or healthcare, don't try to push people to use your model. You just said this is a model with high accuracy. This is a decision making. It's just help you to make a bit more informative decision. Also, SEMA, as you see, if you look at it, although the figure is different, but basically it seems similar steps. So in the sample, basically, you make the data in Explorer, you do visualization, and also some part of data prep. Most of the data prep is modified, so you select some variables, transfer variables in the better format, model and assets. Here we don't have deployments, but I mean, again, if you have a good model, why not? You deploy it later. Also, as you see, we have two direction of links. It just means sometimes you're not happy with some outcomes, you go backward and try to improve your model. KDB, again, similarly, as you see, we have data selection. Instead of data preparation here, this is data cleaning. You transfer your data. In extract pattern, basically you apply your algorithms, data mining algorithms, and if the accuracy is good or any performance measure that you have is good, so you instead of deploying, you use it as a knowledge. So it could be a knowledge, and as you see, in each step, you might go back and forth based on the feedback there. So don't need to memorize these standards, but just keep in mind, all of them are basically talking about the same thing, just in different ways. You're just saying that you have different steps that you need to follow, and based on your outcome, you might in fact go back and forth. So your for final project, don't be upset if you need to go back and forth a lot. It's actually a good thing. So let's say for your project, your accuracy is 70%, and I would look at your project and see you just go back and forth multiple times, but you cannot improve more than 70%. That's okay. So I don't expect all of you get like 95%, 99% accuracy. I just look at your project and think if I get the impression of you guys follow some certain standards and go back and forth, that's fine. And based on different domains, the accuracy are different. I think for heart transplantations, people use predictive model to predict if someone survived after a certain time and after some certain time after the heart surgery, transplantation surgery, and I think those models like 60–70% at most. So
what would you say is a good accuracy level?
For heart transplantation? Or?
No, like in general, if you're talking about prediction models, how would you know if the model has good accuracy level? You
look at literature. So for example, I said for COVID-19, I see many people are could get 93, 94, 95. So if you're around that, that's good. For heart transplantation, so people try to use so many algorithms to predict the survival rate, but they are at most 67. So if you're around that range, that's good. If you can make much better, that's even better. But if, let's say, if a new field and you produce accuracy of 80%, nobody knows if it's good or not. You just see you just go back and forth several times and try to improve the accuracy, but it was 80, so that's it. Okay, so here you can see how people cited standards. So HISPM is the best. I mean, the most cited algorithm in the KD nuggets is one of the websites that you can find data sets. My own means they follow some standards, but they didn't mention it. So in my KDB, some certain organizations have their own standard, but at the end, all of them should have some certain steps, and they go back and forth until they have a good evaluation based on the performance measures that they have. Any questions so far? Let me wait 1 minute, so if your friends over Zoom have questions, they can raise their questions. So I can answer. Let's see, there was one question. No questions. So one of the most used type of data mining method is classification, which I almost say every semester. Most of the projects are in classification. In nutshell, you try to predict your target variable to belong to some certain category or class. Let's say in COVID-19, the target or dependent variable is either somebody has COVID or don't have COVID. So 2 classes. Or heart transplantation, somebody could survive or not survive, 2 classes. Can anyone tell me a problem with more than 2 classes? A classification problem to more than 2 classes? You can just make it up. So let's say I look at the students' characteristics and I try to predict their nationality. So it could be Indian, Chinese, American, other countries. So more than 2 classes. So, but also we have regression. So in regression, you would predict a nominal variable, numerical variable, let's say Bitcoin price. So next day could be 48,049 or 47. So it's a continuous variable. So when we say classification or regression, just keep in mind what do we mean. Also, I already talked about clustering, which should categorize your observation based on some certain characteristics. Like what I said about YouTube. So look at, here I use 2 different, basically I'm showing you visualization of 2 different classification model. So it tries to classify blue circles from red circles. So the green line is much more complex and it's almost has the accuracy of 100% because it classifies blue and red precisely. The black line needs some blue and red points. Or same in the regression. So this is a classification problem. This one is a regression problem. So in the left side, or yours is left. So in the left figure, so the blue line, it's regression, doesn't follow the pattern completely. In the middle one, it somehow follows, and in the overfitting, it just try to go over all the points. Same here, we have the black line is fitted well. The green ones is overfitted. But you might ask me why you're more happy with the black line, and also here you're more happy with the middle one. Basically, we are talking about the overfitting problem. So let's say you have a train set. I talked about Bitcoin price or COVID cases. So usually what happens when you train very well, or let's say not so very well, let's say you overtrain or you do overfitting. So in the train set, you have a very good model that can predict everything very well, either Bitcoin price or like survival of heart transplantation surgery. But the problem, if your model is trained too much under your train set, usually you cannot generalize your model in future use. It's actually the experimental result we have seen. If you overfit a model on the train set, usually it's not very practical model. In future, when you want to, let's say, if you want to predict the Bitcoin price in the next day, or if you want to predict a new patient has a COVID or not, usually they don't fit very well because they are very specialized on their training set. They are not good for generalization. Having said that, usually if you use too many variables for your model, let's say use 40, 50 variables. Usually in those cases, you have overfitting. You have a good prediction performance on the training set, but in the test set or future cases, you don't have a good model. So therefore, which is these are all based on the experiences. I don't have any mathematical proof for them. But usually if our model have 4 or 5 variables, we are more happy than using 20, 30 variables, because when you have too many variables, your model overfit on your training set. So you might see in the new publications, people try to use more simpler algorithms with less amount of variables, because they more focus on the practical aspects of their data mining. They don't want to have a good prediction performance on the train set, but they cannot deploy their model for the future. I think I already talked about train and test set, so or validation set. So it's not always the case, but usually at the beginning you have a historical data. That could be historical Bitcoin price or historical COVID cases. You divide your data in 2 sections, or sometimes, let's say 2 sections. So one section is for training your model. The second section is for validating your model. So you look at the performance of train set and validation set. And you want to see if your model is good in both. If it's good in both, you're less suspected that you have an overfitting, because you randomly divide your historical data into sections of training and validation set. Then we introduce a new data, we call it test set. So historical data divided into 2 sections, training and validation. You introduce a new data set from other sources, we call it test set. And when you look at the performance of our model in all of these 3, in train set, validation set, and test set. If we have high performance in all of them, or maybe high accuracy, and they are pretty close, you would have a good model. So let's say you don't want to have a 95% in validation set and train set, but having 70% in the test set. It just means maybe your model is overfit on the historical data, but it's not good for the future data, because in the future, it changed from 95 to 70. And this is another experimental figure. So we have seen, I just said, if the model is too complex, the differences between error in the train set and prediction set is too high. Also, if your model is less complex, there is a less differences between, let's say, train set and test set. But usually, if you have your number of variables is very low, maybe 2 variables, the over accuracy is low. So at the same time, we want to have a higher prediction performance. Also, we don't want to have such a gap between training error and new data error. We want the gap to be very close. So if you have a closer gap, it means you have a more practical model, because in future, with new data, there's not that much of big differences between what you already saw in the historical data and in the new data. I think I talked a lot in the last few slides. I just want to see any questions about complexity, train set, validation set, and test.
Professor, when you're choosing a model for your data, you said that it's it's not always better to choose a more complex model or more flexible model. So if we want to know which is the best model to use, do we have to always, test all the models and then reach like the validation step and then only, which model is the best? Or is there a way to like just look at our data and know?
Actually, I have a paper how to find the best combination of them, but I think it's very complex. So, but usually, I mean, my paper has some objective way of doing that, but usually 99% of the time, and in more practical case, people have some previous experiences, which type of models is good for some certain problem. Maybe for Bitcoin, logistic regression is the best one. Maybe for transplant surgery, SVM is the best one. So some of it comes from experiences, but again, what I saw, people try different combination of models to see which one has the best performance. So in overall, we look at the hit rate or accuracy. You don't have to. In more practical case, and not your class, we will also look at the speed of the algorithm. So sometimes they want to have quicker decisions, so they look at less complex or faster algorithms. For example, I think one project I've seen the different, but it's not always the case, but at least in one experience I've seen that deep neural network is 100 times slower than logistic regression. It was in one of my experiments. So if your time is not tight and you have a couple of days, you can try all type of algorithms. But if you want to make faster decisions, you look at the higher speed algorithm with higher speed. Or let's say for your project, your laptop is very old. You don't have to work with SVM or like a deep neural network that are very time consuming. Maybe you can use a faster algorithm such as logistic regression. Okay, transparency and explainability. So if you use a statistical model, let's say logistic regression, decision trees, naive Bayes, everything is very transparent and you can easily talk about the relationship of variables and steps of your algorithm. On top of that, we have some algorithms we call usually black box algorithms, such as neural network, SVM. Although with some new researchers will try to explain those what is under the hood of those algorithms, but in general, we consider them as a black box algorithm. So it's very hard to talk about the relationship of variables and also internal calculations. However, we are still using those black box algorithms because their prediction performance or accuracy is very good. If you can have a very high accuracy with a transparent algorithm or a statistical algorithm, it's actually better. But in many cases, you don't look at transparency, you look at the prediction performance. So there's some trade-off of using them one, but usually people are more towards transparent algorithms that they can explain all relationships. Okay, you have another next assignment. So I need you guys to just Google and find the differences between black box and white box models. And just provide some examples for each. So let's say just tell me some sample black box algorithms and white box algorithms. I already actually I just talked about them a little bit, but I think many will be fine. Also, here I took a video from one of my colleagues. He talked about decision tree and he explained the relationship. So you can consider the white box algorithm. Just later, if you are interested to know more about decision tree and how to interpret the decision tree model, watch this video. This is actually a good video. Just keep in mind, we have different types of prediction performance, like I just skip through them because I'm not sure you know about accuracy, positive rate, true negative rate, precision, recall. So you have in your final project, and you guys talk about accuracy, sensitivity, specificity. So I want to see if your model is good for both negative rate and positive rate, how your model performs. Okay. Here I'm talking about, I'm just thinking some concept. So I talked about test set, train set, and validation set. So there is no biblical rule, but usually your train set maybe should be near 60, 70%. Maybe you consider 20% as validation set and the remaining 10% as a test set. But you don't have to follow the rule, just generally keep in mind. Because your data, you don't have any future data. Usually when you download it, you just have a large data set. You can just randomly split in the test set, train set, validation set, and test set. Another performance measure is around area under the ROC curve or AUC. It's for two-class classification. Let's talk about Titanic. So if somebody survived Titanic crash or not, or Titanic disaster or not. So what happens? Usually, in all the cases, actually, the outcome of the prediction is a number between 0 to 1. It could be 0.1, 0.2, 0.3, up to 0.99, up to 1. So, and we consider threshold. Usually, threshold is 0.5. So let's say outcome or predictive algorithm is 0.4. It's less than 0.5, I would say this guy, I predict as a die at there. If the outcome of my model is more than 0.5, I would say survive. So I have a threshold of 0.5. What if I change my threshold instead of 0.5 to 0.2? I had 0.4 and 0.6. Both of them are more than 0.4, 0.2. So I would say both of them are survive. So as you see, based on the threshold, you might have different prediction. AUC is just talking about that. So in AUC, you change the threshold from near to 0 to 1. Then you look at false positive rate and true positive rate. And you make it curve. So I know it looks a little complex, and you don't do it manually. I'm just saying what happens within your model. So the area under that line could talk about the performance of the model. So if the area under that line is near to 1, means you have a really good model. Your model is very good in predicting both death and survival. If your area under the curve is near 0.5, it just means you don't have a good model. It's just similar to tossing a coin around and say which one died, which one survived. So again, this is how they make the line and how they calculate the area under the line. So they use some. If you had some mathematics course in your undergrad, you might know integral. So they use integral algorithm to calculate the area. But again, you don't have to know exactly how they calculate AUC. Just keep in mind, if your AUC is near 1, it means your model is very good at predicting both cases into class classification. If it's near 0.5, it means the performance of your model is not good. It's what you need to know, but I just told you how they make those curves and how they calculate things. For example, here is 0.84, so it seems to be a good AUC. Okay, so I know some of this concept might be boring for some of you, but you might already have in other classes. On top of like talking about train set, validation set, and test set, you can divide your data in two sections, train and test. Then you divide your train set into some equal subsets randomly. For example, here we already we already put our test set somewhere else. Now, for the remaining of data, we divide the whole data set into 10 equal sections. So here we have 10-fold is 10-fold cross validation. So each time you pick one of those 10% as your validation set, and you train your model on the remaining 9 sections or segments. So after training your model on the remaining 9 sections, you predict the leftover section, so leftover 10%, and you report your performance. Next step, you change that, you put that segment back, you pick another one as your validation set, and again, you train your model on the 9 sections and predict the performance or predict the segment that you took it out. Therefore, if you have 10-fold cross validation, how many times you train and validate? Each time you pick one. So, 10 times. Yeah, so if we're talking about 10-fold cross validation, I talked about just training and validation. In that one, you randomly divide your data in 2 sections. Here, you divide your data in test section, and instead of just having one train, one validation, you have 10 train and 10 validation. All of this effort is just for being sure that you don't have overfitting. So just look at the first picture. So, or first figure here. So in the first figure, I used the 9 segments for train and 1 segment for validation. Then I look at performance and see what's the gap. If the gap between train and validation is good, I said, nice, thumbs up. Then I check the second sequence. I randomly take that, train, validation, and I look at the performance. Is it close or not? So you might say, what's the point of doing 10-fold cross validation? So instead of just train 1-fold, you are doing 10 times. It's just for extra, to be very sure, to be extra guarantee that you don't have overfitting. So later when you introduce a test set, you hope that this error would be minimized. So don't be worried. So you don't do these things manually. It's just some module you just drag and drop, and you see the report. So you see the report of 10-fold cross validation. You see how's the performance, and also you look at the performance of test set. And in your final project, you just report, yeah, I use this module for 10-fold or 5-fold. So you don't have to have 10-fold, maybe 5-fold is enough. But the idea is same. You look at the performance of each fold on each validation set and test set, and then you end up saying that if you are happy with the model or not. Let's say if I do 10-fold cross validation, I train 10 times and validate 10 times. Let's say if my accuracy one type is 95, another one 85, one 70, again 95, 90. So there's a huge difference between 95 and 70 different folds. It seems you cannot generalize your model. But if in all those 10 validation set, my prediction performance is something like 95, 94, 96, pretty close. It seems I have more reliable model, which I can generalize it for future use. Yes.
In the previous graph that you showed, so the ideal situation would be that both the lines are running parallel to each other.
Usually it never happens, but we just want to have a very close gap. The best, they overlap completely, which never happens.
That should not happen. It should not come too close to each other.
If closer, better, but usually doesn't.
Narrow down.
Yeah, narrow. We want the gap to be narrowed. Also, we have a leave one out algorithm. So if you have enough data, so you can do tenfold classification. But let's say your data is like just 20. It might be some rare cases you don't have that much of observation. So in those cases, instead of dividing your data, 5 or 10 sections, which is not practical, each time you take out one sample as your validation set, and let's say you do the remaining 4 traces. Leave one out. So it just means you don't have that much of observation, but you have to do some prediction. So we try to use less amount of observation for some prediction. This is not ideal. Also, bootstrapping, which you randomly pick some data, do prediction, put it back. This is for cases that you don't have enough observation. For low number observation, instead of dividing on 10 equal sections, maybe you do 100 times. You pick some small sample, do validation, put it back. I think I already talked about the. Also, take care of multicollinearity. So sometimes some of the independent variables are highly correlated to each other. We try to avoid that. So most cases, it needs some background knowledge. So people might say, let's not focus on those variables. For example, for house price prediction, maybe number of bedrooms and house or your home area is highly correlated. So in those cases, sometimes your outcome looks crazy. For example, some regression coefficient should be positive, but they turn out to be negative because those variables just affect each other. So especially for a statistical prediction or white box model, you should avoid multicollinearity because it just damages your performance. Also, it's very hard to interpret your parameters. Okay, I think that I'm ran out of time. Please watch this video. It's really important video. I think since it's important, let's watch it. I know it gets out of time almost. So I think the remaining after this video, there's some optional readable decision trees. 9 demo, which happens next class. So let's watch this video. I think this is an important video that just keep in mind for your final project. It's talking about causation and correlation.
Hello, I'm Paul Henney, and I'm a philosophy graduate student at Duke University. And in this video, I'm going to talk to you about correlation and causation. Maria and Andy are high school students in Arizona. Andy always gets an A on his math test when it's sunny outside. On one sunny day, before Andy goes to math class, he tells Maria, "I'm going to ace this test today because it's sunny." Maria objects. "No, Andy, you'll not ace this test because it's sunny. You'll ace this test because you studied. The fact that it's sunny outside has nothing to do with it." Andy responds, "But Maria, I always ace my tests when it's sunny." Maria replies, "Okay, sure, but that's just because you always study for your math tests, and it's always sunny here in Arizona. The sunniness does not cause you to ace the test. Maria's correct. Andy's making a mistake, right? The sunniness doesn't cause Andy to ace his test. The two events, the sunniness and Andy acing his test, occurred together without one causing the other. In other words, the two events are correlated in some way, but there's no causal relation between them. Andy's reasoning here is fallacious. Simply because two events are correlated does not mean that one caused the other.
So keep in mind how you talk about the variables on your final project. So some variable could be correlated, but doesn't make sense that you see something cause something else. For those cases, actually there's some statistical methods for that. It's active content for this class. But for your case, maybe you can do literature review or use domain knowledge. So knowing some domain knowledge helps you to avoid this trap.
This conflation of correlation and causation is what we will talk about in this video. First, let's consider some other examples. Fido barks when his tail wags. People with higher grades in college have higher grades in high school. People who take vitamin C recover more quickly from a cold. These are correlations. That is, there's a correspondence between these events. For example, the dog, Fido, barks when his tail wags. But there's no reason to suspect that there's a causal relation between these events. While these events often occur together, there are many times when Fido's tail wags and he doesn't bark, and there are times when Fido barks but doesn't wag his tail. Furthermore, we may suspect that there is some common cause for these events, like Fido's excitement when his owner comes home. Now that we can agree that these are cases of correlation without causation, we can discuss two types of correlation, positive and negative. In the next video, we'll discuss how these types of correlation specifically relate to different types of causation. But for now, let's just introduce them. When events frequently occur together, like in the examples above, they are positively correlated. If two events are positively correlated, then when one event is present, the other is often present as well. In our first example, it being a sunny day in Arizona is positively correlated with Andy succeeding on his math test. On the other hand, two states are negatively correlated when it's likely that when one event occurs, the other will not occur. For instance, when it snows, it's often not very sunny. So snowing and sunniness are negatively correlated. We often hear about positive and negative correlations, especially in the news. Headlines like, "Taking vitamin C helps you recover more quickly from a cold," indicate positive correlations. Taking vitamin C is positively correlated with recovering from the common cold more quickly than if one had not taken vitamin C. Or headlines like, "Eating more nuts makes you less likely to have higher levels of bad cholesterol," indicates that eating more nuts is negatively correlated with having higher levels of bad cholesterol. You may have heard headlines like these and had conversations with some friends about them. And you may have heard someone say something like, "Awesome, so I'll just eat more nuts and get rid of my bad cholesterol." You may have also had the experience of someone else saying, "Yeah, but that's just correlation, not causation." Of course, this person may just be a jerk, but they are right to point this out. Unless you had evidence that a causal relation held, it is a mistake to suggest that this correlation is actually a causal relation. So it'd be wrong to say that eating more nuts will cause you to have lower levels of bad cholesterol, unless you had evidence that the causal relation held. So let's consider an example where two events are positively correlated when neither causes the other. Consider this again. People with higher grades in college have higher grades in high school. Here, earning higher grades in college is positively correlated with earning higher grades in high school. Now, it's incorrect, as we've discussed, to claim that earning high grades in high school always causes someone to earn high grades in college. Nonetheless, earning high grades in high school may sometimes cause a person to earn high grades in college. For example, Jane may have gotten good grades during high school, and some of those grades transferred to her college, which causes her success in college. Here, success in high school for Jane causes her success in college. But most of the time, it is not the success in high school that causes success in college. It is usually someone's working hard in college courses that causes that person to succeed in college. And at that type level of the statement, where we are identifying a correspondence of two data sets, the causal claim is false. So again, the two events, high school success and college success, are positively correlated, but they do not cause one another. When two events are correlated, it may seem that one causes the other, but there may be alternative explanations we've ignored, like working hard in college courses causes that person's overall success in college. So it's fallacious to conclude from only the fact that two states are positively or negatively correlated that one causes the other, because there may be another cause that explains the outcome. It may be that there's a common cause for both of the events, or that there's some alternative cause altogether. On the other hand, the correlation might just simply be a coincidence. But this explanation and other questions will have to wait for part 2, where we will talk more about the analysis of cause.
So just keep in mind how to interpret the result of your research. Looking at this video. I'll also talk about multicollinearity. Sometimes if there's a multicollinearity and you are using statistical models, the correlation would be ruined. So you expect some positive correlation, negative correlation, but because of multicollinearity, some of them would be in opposite way that we expect. Okay, that's for today. Thank you very much, and good night.